right-tailed. Okay. What would we say a central value would be? Okay. So when I talk about central values, think of if I were to cut this out, this piece of wood that has this shape, and if I were to try to balance it on a seesaw, where would I want to put the fulcrum? Where would I want to put the triangle?
What's the peak?
Around here? Does this look good? Okay, so it looks like if I put it there, it might be balanced. Okay, so the balancing point we can think of as is actually the mean of the data. Okay, but we can think of it as the center. Okay, but the mean is the balancing point, and I'll write that definition up in a little bit here. So what does it mean to have a right-skewed distribution? A data point that's out here, what can we say about it? It's very high, but it's uncommon. Okay? But we are, we're about this far above the mean. Okay? So we have values out here with values that are much higher than the mean. Uncommon, but they exist. Okay? So uncommon, but values exist. Much higher than the mean. What if we went that far below the mean?
Would be no value.
No values. So if I try to go this far below the mean, I'd be out here, no values, equally distant below the mean. Can we think of any numeric distributions or numeric variables that might be right skewed? Age. Income. Income is a very good example of a right skewed distribution. Okay? So if we think of average household income in the United States, do you guys have an estimate of what that is about? I guess it depends who you ask, but it's around 50, 55,000 for average household income. Okay? Someone out here would be someone with an average income of maybe $1 million a year. Okay? Are there people with $1 million a year annual income? Yeah, not a ton, but there are people. Okay? We call them the 1%ers or whatever. They're out there. Okay, $1 million per year is like $950,000 above the average annual income. Does anyone exist with that's $950,000 below the average annual income? No. Okay, so we can be this far above the average, but if we try to go that far below, that would be someone making negative $900,000 per year, which I don't think is possible, but I don't know. Well, let's just say, wage earners, okay? Maybe, I don't even know. Okay, so generally we say the lowest income that's possible would be 0, okay? All right, and so we have a right skewed distribution because, yes, you can be have high values way out here, maybe not common, but they do exist, whereas if you tried to go the other way, it's impossible, or nobody exists that way. Okay. So income, very good example. Human weight, also right skewed. Okay. Average weight of a person, both male and female included, is around 160 something pounds. Okay. We have people who are 400 pounds, not very many, but they exist. 400 pounds is like 240 pounds above average. Does anyone exist that's 240 pounds below the average of 160? No. Okay. Also right skewed. Alright. Okay, if that one's skewed right, what would this be?
Skewed left.
Skewed left. Okay. Skewed left, also unimodal. Anyone think of something that could be skewed left?
IQ.
I'd say IQ is symmetric. Test scores, okay? Maybe the average is somewhere around here, 80-something%. You're not going to have people over 100% if this is not graded on the curve. Are people going to be scoring 20%, 30%? Probably, okay? Maybe not very many, maybe not in this class. But you will have people with test scores much lower than average, whereas on the other side. Okay. So that's left skew and right skew. And then as for peaks, we saw unimodal, but you can have two peaks, and this would be bimodal. It doesn't have to be nearly symmetric as this one is. This would also be bimodal. And anything more than that, we would just generally call multimodal. Any suggestions as to what might be multimodal? Or bimodal?
Car accidents
Car accidents?
with age.
Okay, so we're only looking at one numeric variable at a time. Okay, so to say car accidents with age, that would be more apt to something like correlation where we're looking at two numeric variables. So here we're just looking at one. Bimodal, classic example that I always use would be testosterone levels in people. Okay, so if we just threw everyone together and we just said, we had you spit in a cup, and then we sent your spit to the lab, and they sent back the amount of testosterone recorded in your spit. It would come back looking like this. What's over here? High testosterone. And over here? Low testosterone, okay? So everybody produces testosterone in their body. Over here we would have the middle of this peak would kind of be the average amount of testosterone in a male, okay? Some men produce more testosterone than other men. Some men produce less testosterone than other men. But in general, this is the average, and this is what we would see. This would be the most common values here, okay? Over here, this would be what? For the women, okay? About the average level of testosterone for women over here. Some women produce less testosterone than other women. Some women produce more testosterone than other women, okay? But in general, women with high levels of testosterone generally still have less levels than males with low levels of testosterone, okay? And so you would see a bimodal distribution, okay? This is a numeric variable where, I don't know how they measure testosterone. It's like milligrams per deciliter or something like that. And you'll have a wide spectrum, but you'll have kind of a peak for the men and a peak for the women, or whatever, in any example, whatever subline thing goes with that. Okay. This is actually how they determine whether you are a man or a woman if your gender is called into question by the Olympics or something. Okay, so I don't know. because it's not so simple as it used to be, all right? You would think just that whether you are a man or a woman is clear, but it's not always the case. So that's what we have. Okay. So describing shape, number of peaks, unimodal, bimodal, multimodal, and then shape. Symmetric, left skewed, right skewed. The book mentions exponential. I'm not too worried about that. Okay, we can describe the center. And we can use the mean or the median. The mean is probably the measure of average that you are already familiar with. Add up all the numbers, divide by how many numbers you have. And so we would say the symbol for mean is y bar. And it's given by this formula. This thing that looks like an E or a sideways M is sigma, and that means add, or sum. So add up all the different values. So in this case we say add up all the different values of y, divided by n. What is n again? Sample size, okay? So add up all of your numbers, divide by your sample size, or how many you have. That gives you the mean y bar. The mean, like I said earlier, is the balancing point in your data set. The median is the middle point. The middle point. Half of the points are larger, or half of your data is larger than the median, half of your data is smaller than the median. If you have, and you've probably learned how to calculate the median, and it might say, what do you do? What's the first thing you do? Okay, well, alright, so let's just talk about this. Alright, so finding the median, the first thing you do is you put the numbers in order from least to greatest. And then you find the middle point, all right? And so if you have a bunch of numbers, you could start on the ends and go and then you go into the middle, all right? That's one way to get the median. But if you have a whole bunch of numbers, that might not be a practical method. So the median is the number in the n plus 1 divided by 2 position. Okay. It's not, the median is not n plus 1 divided by 2. It's the number in the n plus 1 divided by 2 position. So let's try a short example. And I'm going to use this set of numbers a couple times tonight, so it might be worth putting in a location that is easy to see. Alright, so let's say I've got a bunch of numbers, 14 numbers. So these are, so let me just give you the context for which these numbers come from, okay? We put some radish seedlings, and we planted them, and then we exposed them to light, and we saw how much did they grow, okay, over, I don't know, like a week period or something, okay? And we measured how much they grew in millimeters. And so one radish grew 3 millimeters, another one grew 5, and another one grew 5, and then I'm listing off all of the measurements from all 14 of them. These are already put in order, so don't forget this step, although I've already done it for you. If I told you to make a histogram with a bin width of 3, could you do it? Yes? No? Okay. Well, maybe at the end of class, if we still have time, maybe we'll do that. Okay, so here I've got 14 numbers, each representing how much a radish grew in light. And I'm looking for the median height. Alright. So one way is I could go, start here, and I can go, and then work my way in, okay? And that could work. The other way is I could use what I've written here. The median is the number in the n plus 1 over 2th position. So what is my n here? N is 14. I'm pretty sure I put all 14. 6, 7, 8, 9, 10, 11, 12, 13, 14. Good. N is 14. So what is n plus 1 divided by 2? 7.5. Is that okay? So if I label these, if I say this is my first number and this is my second number, I would have 3, 4, 5, 6, 7, 8, 9, 10. My 7th place number is 9, and my 8th place number is 10. So what is the number in the 7.5 position? It would be halfway between 9 and 10. Okay? So the 7.5 number is halfway between 9 and 10. Okay, so what number is halfway between 9 and 10? 9.5. So 9.5 is my median. Yes?
If the numbers would be, I guess, not as easy to get the half of, like if they were 9.674 and 10.123.
Okay,
Would you just
so
average them?
yeah, you would take the numeric mean of the two central numbers. Okay, so if it's not so easy to figure out 9.5, you would take this number and divide by 2. Okay, so or take the mean. If I asked you to calculate the mean, that would be straightforward. You would add up all 14 numbers and divide by 14. Okay, and that would not be too challenging other than making sure you typed in all 14 numbers correctly. If we had an odd number, so if I didn't have 21 and we only had 13 numbers in our data set, what would my median be?
9.
9. It would be the number in the 13 plus 1 over 2th position. It would be the 7th place number, and in that case, it would just be the number 9. Good? Good. All right. So that is the median. So we've talked about the mean and the median. It is good to know that the median is resistant to outliers. Meaning, if the last radish grew 50 millimeters or something, the median would not be affected by that. It doesn't care, because it's in the middle. It would still be 9.5. However, the mean would be affected by that, because the mean would include that last number. You would add them all up, and when you divide by 14 or whatever, the number is much, much larger. Is one better than the other? And the answer is no, it all depends on your circumstance, okay? So, the median is resistant to outliers, whereas the mean is, quote, drawn in the direction of the outlier. Outliers, or what we call the tail. Okay, where did we see that word tail before?
In the skewed graphs?
In the skewed graphs, okay? So when it was right skewed, the tail was on the right side, okay? So right skewed looked like this, left skewed looked like this, okay? So, and if you need help remembering, so right skewed looked like this, and if you need to remember that this was right skewed, just imagine if you were to cut this out of the board and stab someone, which side would you use to do the skewering? You would use the right side, okay? So the median would be somewhere in the middle, whereas the mean gets pulled out towards the skew. Okay. So that's worth noting. So we've got the mean and the median to describe the center. Once we have the center, we might also be interested in what we call the spread, or dispersion. Dispersion, or spread, is a way to quantify how similar or how different the values that you see are. Okay, so just imagine two families, okay? Two large families, all right? In both families, the grandparents have 4 kids, and then each of those 4 kids each had 2 kids of their own, or something. So there's a total of 8 grandchildren. All right, and in one family, the ages of the grandchildren are so, in order. So that's one family, the 8 grandchildren are like that. And then in the other family, the ages of the grandchildren are like this. Can we both imagine families that look like this? Yeah, it's very possible to have grandchildren where the oldest is 23 and the youngest is 1. It's also very possible where the grandchildren, where you have 8 grandchildren, where the oldest is 9 and the youngest is 6. Alright. So if we talk about the spread in ages, which family would we say has a larger spread? Let's call this family B. We'll call this the Adams family, and this would be the Baker family. Alright. So which family has a larger spread? The Bakers. Okay, so the Bakers have a larger spread others have less spread, smaller spread. Alright, and so we can imagine, you know, what do the family gatherings at the Baker family look like? Well, you're going to have, you know, older kids and younger kids, and they're all kind of doing their own thing, and everyone, I don't know, maybe they all hang out together, but they're all doing different things in life, okay? Whereas in the Addams family, you can just imagine this chaos of all these children of similar age running around. They're probably good friends. They know each other very well and things like that. They've probably grown up doing the same types of things together. So let that be a picture of the concept of less spread and more spread to you, okay? Obviously, we're not always going to be talking about the ages of children, but you might have numbers, okay, different data sets where you have, I don't know, washing machine part tolerances, okay? And so, you know, some manufacturer might have a wide spread of, you know, the parts might have a wide spread in you know, the weight, and in the other cases they might have a tight spread. You know, probably the higher quality machines would have the ones with a small spread, whereas the lower quality machines might have a wider spread and things like that, okay? So we have a way to quantify these things, rather than just saying this has large spread and this has small spread, which is only useful in a comparison context. We can quantify the spread for any set of numbers, okay? And we have a few ways to do this. One is the range, which I think many of you are familiar with. Another is the interquartile range. Also known as the IQR. And lastly, we have the standard deviation. Which you've probably all heard of, but maybe less confident about the meaning of. These are all just ways to quantify spread. So rather than just saying there's large spread over here and small spread over here, we quantify them using the range. The range is the largest point minus the smallest point. So the range is equal to the max minus the minimum. So in the Addams family, the range is 3 years. 9 minus 6, we have a range of 3. Whereas in the Baker family, the range is what? 22. The interquartile range is the difference between what we call the third quartile and the first quartile. So I have to define what quartiles are. Quartiles, there's 4 quartiles. The first quartile, second, third, and fourth quartile. 25% of the data is smaller than the first quartile. 50%, or 2/4, are smaller than the second quartile. And 75, or 3%, 75% or 3/4 are smaller than the third quartile, and all data, or 100%, 4/4 is smaller than the fourth quartile. What's another name for the second quartile? The median. Okay? The median is the second quartile, because we established that the median is the halfway point. Half of the data is larger, half is smaller. So the median is the second quartile. What's another name for the fourth quartile? The max. The max is the fourth quartile. So really the quartiles that are of interest to us are Q1 and Q3. Okay? Well, we learned how to find the median, and that is the first step in finding the quartile. You first have to find the median. Okay, so you find the median, which gives you Q2, or the second quartile. And so once you find the median, so I'm going back to this data set, essentially to find the other quartiles, is you pretend that this is a shorter list, and you're going to find the median of this, and that will be your first quartile. That makes sense? So you're just chopping it in half, and then you're taking each of those and chopping those in half, and that will give you quarters. So what is, if I look at these numbers, 3 through 9, what is the median of this list? 7. It would be the fourth place number. This would be the quote-unquote median of the lower half, and that would be Q1. Is that good? Okay. And I do the same thing over here, and so that would be Q3. Okay, so in this data set, my IQR, my interquartile range, is 10 minus 7, Q3 minus Q1, and an interquartile range of 3. Is that okay? The standard deviation has a more complicated formula to find its value. I have recorded a video and posted it online. And your homework this week will include watching that video on calculating the standard deviation. But the important thing to remember is that it is just another measure of spread. Okay? We have the range which is equal to 3 over here, and the range which is equal to 22 over here. I can calculate the IQR over here. The median is right here, and then so Q1 is right here. Q1 is equal to 6, and Q3 is equal to 8.5. So I have an IQR of 2.5. I know I'm doing this quickly. Same thing over here. The median is between 7 and 12. My Q3 is between 18 and 21, which would be 19.5, I'm sorry. And over here, Q1 would be 4.5. So my IQR is 15. IQR is 19.5 minus 4.5. I have an IQR of 15. So in both cases, we can see the range and the IQR for the Baker family are much larger than the range and the IQR for the Adams family, indicating that the Baker family has a larger spread than the Adams family. If we were to follow the standard formula for calculating the standard deviation, we would also see that the Baker family has a larger standard deviation than the Adams family. Again, the formula and way to find the standard deviation is recorded in a video for you guys to watch and do this week during your homework. Okay? With the IQR, we can create another visualization. So like a histogram and a dot plot, we have another way to visualize our data, and this is called a box plot. And a box plot can be thought of as like a cliff notes, just the bare essentials of the data. It basically will show you Q1, the median, and Q3, and essentially the smallest and largest data points that we don't consider outliers. So let me just show you how to draw a box plot. So with a box plot, you first need to go through your data and figure out Q1, the median, and Q3. And we've already done that, and we have 7, 9.5, and 10. Like a histogram, like a dot plot, the horizontal axis contains values that our numeric variable can take on. So on the low end, I would want to at least start with 3. Showing values that our numeric variable can take on. And I'm going to draw 3 lines at each of, or 1 line at each of these 3 points. Okay, so I would draw a line at 7, indicating Q1, a line at 9.5, indicating my median, and a line at 10, indicating Q3. And these 3 lines form my box. So this is the core of our box plot. Q1, median, Q3. Okay, you would not normally label these when you draw a box plot, but I'm labeling them for you there. What is the width of the box?
3.
It's the width of 3, that's correct. What is a word that we have for the width of the box? The IQR. The width of the box is Q3 minus Q1, which is the IQR. Okay, so by seeing how wide the box is, we get an idea of our spread already. Okay, so it's especially useful when we have multiple box plots to compare. We can look at the width of the box and get an idea of comparing IQRs. All right, and then I will show you how to draw the what we call whiskers, or the box, which will give us an idea of the range. Okay. So I'm jumping to what we already call a modified box, what the book calls a modified box plot, but I think in most circumstances they just call it a box plot. So every time you see a box plot, in most cases, it's what our book happens to call a modified box plot. Basically, we are going to try to distinguish between what might be considered normal data and outliers. And this is not the end-all be-all rule of how to establish what an outlier is, but it's a very good rule of thumb. And essentially what we're saying is, if it's more than 1.5 IQRs, or more than 1.5 times the width of the box away from the ends of the box, so if this is the width of my box, and 1.5 that is about this, and so if it's more than this far away in this direction, we will consider it an outlier. And 1.5 if I go this way. And if it's more than this far in this direction, we'll also consider it an outlier. Okay? Is that visualization kind of okay? So we're creating these invisible boundaries, which we call fences. And this is the boundary between what we would consider a normal data point and what might be an outlier. Okay, so the fences, we have an upper and a lower fence. Is given by Q3 plus 1.5 times the width of the box, 1.5 times the IQR. The lower fence, we start at this end of the box, Q1, and we go 1.5 times the IQR below that. All right. So where do I end up with my fences? Q3 is 10. My IQR is 3. So 3 times 1.5 is 4.5 plus 10 takes me to 14.5. I do that on the lower end, and I do 7 minus 4.5, and I get 2.5. Is that right? Okay, so I'm going to draw an invisible boundary. You would not do this when you draw a regular box plot, but I'm doing this here. And I'm drawing an invisible boundary at 2.5 and at 14.5. Okay. And that will be the distinguishing point between what we would consider normal versus outlier. Okay? So I look at my data, and I have to classify which ones are normal and which ones are outliers, okay? So what data points would be considered outliers? 20 and 21. So anything that's larger than the upper fence would be considered an outlier. And do I have any outliers on the lower end? I don't have any outliers over here, okay? So these would be considered outliers. Alright, and so I would draw, indicate my outliers by drawing circles or stars where they go on the box plot. And then I draw whiskers or lines to the largest and smallest data points that I have that aren't outliers. So in that case, what is the largest point that I have that's not an outlier? 14, the largest point I have, basically inside the fence, is 14. What's the smallest data point I have that's inside the fence? 3. Okay, so this is what my box plot would look like. So all of the steps on creating a box plot of your own are detailed in the book. And, but importantly, if you were to see a box plot, can you identify things like Q1, Q3, the IQR, the max, the minimum, things that are outliers? Okay, so good luck as you guys do your homework. We'll see you guys next week.